right here. Okay, so a couple things. So now that we're back from spring break, one of each. Homework 6, it was due on Wednesday. I've decided to push it back until next Monday, okay? Because we haven't had time to cover everything necessary for the homework, so I'm going to push it back. A couple things, though, okay? That doesn't mean start Sunday night, Sunday night at 9 p.m. or something. Problem 1 and problem 2 on that homework you can do right now. And I advise to at least get a good start on it because we're going to have class today, we're going to have class on Wednesday, and we're not having class on Friday because of the Virginia's conference. So I would say, Wednesday is really the only time you're going to have to ask questions in class. So I would at least give it the once-over right now. Okay? Sound good? Yes?
How far are we supposed to plot?
That's a good question. Plot from a KL over R of 0 to a KL over R of 200. Okay? And you don't need, like in Excel, you really don't need to do like 0, 1, 2, 3, 4, 5, 6. You could do in increments of 5 and be just fine. Like 0, 5, 10, 15, 20, 25, 30. You could do that. There's nothing wrong with that at all. Okay? Does everybody understand what I'm saying there? On problem 1, you are to plot an equation in Excel. Essentially, you're plotting the AISC column curves. So you'll have KL over R on the x-axis, and on the y-axis, you'll have your phi F critical. And just make sure that you're going from 0 to 200. And you'll see you'll see what happens when the curve's done. You'll kind of see what it looks like. And anything past 200 really wouldn't tell you anything. But you'll see. Anything else? All right. One other thing I'll point out for the next, I'd say, we don't need one today, but maybe for the next couple lectures, you probably need to bring a straight edge, okay? The reason why is you all have that moment frame alignment chart that I showed you. The way it works is, and we're going to go through this in detail later, but you're going to locate a value here on the left and a value here on the right. And you're going to kind of draw a straight line. So you need a straight edge to know what the K is in the middle. So make sure you're bringing a straight edge. So yeah. Sign-in sheets going around. All right. Sound good? Okay, something doesn't make sense. I just noticed something. I've got 2 handouts of 2, 3, 4. I've only got 1 of the moment frame alignment chart and 1 of flexural beams part 1. Did somebody only grab a couple? There were 6 handouts, so somebody only grabbed 2 of them. You all can go through it. Okay. All right. So I know it's been a while since we've talked about a lot of this stuff, so I'm going to kind of take it slow, but I want to get back into the process for column analysis because we need to start getting into the world of column design. Okay. So let's sort of recap a couple things. So number 1. When we do column analysis, remember we have a number of different means at our disposal to compute the capacity of a column, but it all starts with determining whether or not local buckling governs. So if you recall, we look up the BF over 2TF and the H over TW for a given wide flange, compare that against the given limits to see whether or not the flange or the web is going to buckle as opposed to the entire cross-section. Sound good? And then when we do that, we recognize, okay, we're in section E3, we've got 3 different means that we can use to compute column capacity. And if I remember correctly, we did the first 2, but we didn't do the last one. Am I right? They got that in their notes? All right, we'll go through it in a second. Okay, so method 1 is to use the column curve, which is this equation right here. This is essentially what you're plotting in Microsoft Excel on problem 1. So your capacity is phi times F critical times your gross area. Phi is 0.9. F critical, though, is not like with tension members where you just look it up. You have to compute it. So it's a function of your slenderness. Slenderness is KL over R. If your KL over R is less than or equal to your limiting value, then here is your stress, the 0.658 raised to that exponent times Fy. Otherwise, you're in the elastic buckling range, and it's 0.877 times Fe. Remember, this is inelastic buckling. This is elastic buckling. And the only term that's not defined there is F sub E, and that's your elastic, your Euler buckling stress. So it's just pi squared E divided by slenderness squared. Okay. Now, if you look at a wide flange, bless you, remember Rx is always bigger than Ry because Rx is our strong axis and Ry is our weak axis. That doesn't mean we get to ignore the strong axis altogether, because if we're determining capacity, you would think, oh, well, the weak axis is always going to be the one that gives the lowest capacity, so that's the one we always need to check. Well, not necessarily, because depending upon bracing conditions, your strong axis can actually have a larger slenderness than your weak axis. And remember, the larger the slenderness, the higher your KL over R, the lower your capacity. So the long and short of it is you just have to go through and compute the KL over R, the slenderness terms for each axis to determine which one governs. And in fact, we did this example. This is the one that we did. If you look at this given column, this would be broken up into an x-axis model and a y-axis model. That column is braced at different locations along the y-axis, but for the x-axis, it's just a single column that's 35 feet long. So we did this column using the curves, and then we went through and did the table 4.1 analysis, didn't we? Am I right on that? So let me pull up the notebook just to get everybody's memories jogged and whatnot. Notes. Oh, that's already up. Close that. I think I opened the notes twice. Come on. Automatic activation. I'm good. So the only, it's coming back. The only thing we're missing is the alarm in the hall. Then to feel like we're at home, right? What's that? That's what I had mentioned it earlier, and they said, now that you brought it up, it's going to go off, All right, so I think maybe right here. Okay, so we were looking at this example. The first thing that we did is we computed our compactness limits, and then that was good. We did our slenderness calc. Remember, we did it in an incredibly backwards condition. You are like, why are we doing the R first, and then the L, and then the K? It was like, because that's the easiest way to go about it. And then we computed KL over R for each one, and we found that the x-axis one was the one that governed. Then we said, all right, let's take that, go through that rote process of computing our elastic buckling stress, our critical buckling stress, and then the design capacity. Right? Remember, this is the push mower, right? This is the one that takes a little bit of work, but it will handle anything that you throw at it. Okay, so we have a design capacity, and it came out to be like what, 958 kips. This bringing it back. I know it's been a while, but that's why we review this stuff. Okay, and then we went and did this. Now, I want to focus on this a little bit. Now, this was a shortcut where we could look up the capacity. We just said, all right, based on our strong axis KL, we look up that 16 feet, that 17 feet, and then we linearly interpolated, right? But then we had to, where we got that 16 feet and that 17 feet was by computing this effective KL. Remember, KX LX divided by that ratio of RX over RY. Use that to pick our two values and interpolate. And you can see we got effectively the same answer, the 958.12 kips. Sound good? Okay. This next method is going to be pretty quick. So I want everybody to turn to table 4-22. So you should probably tab this one. I find that students, like when given a choice, don't really use this table very much, but this table will save you a lot of hassle, okay? It's a great, I guess the best way of describing it is it's a great gut check. So this is on table, or on page 4-322, and it should say available critical stress for compression members. Okay. Now, one of the nice advantages of this table is, first off, it will handle multiple different yield stresses, right? I mean, we got 36 KSI, 46, 50. It handles quite a number of different yield stresses. So that makes our life a little easier, okay? And here's the long and short of it. You just go into your table with a KL over R. In this case, let's say we have 86. Bam, there's your stress. Multiply that times the area. There's your capacity. What? All right. One, I guess, caution, if you will, to using this table, and this is the mistake I see students making more than any when they use this table. When you look up a value, you are not looking up F critical. You are looking up phi critical. Okay? So phi is already incorporated. So if I wanted to determine the capacity of a column, I look up that stress and I multiply it times the area, and that's it. I don't multiply by phi again because phi is already there. So a lot of times, students, what they'll do is they'll say, okay, here's the stress, multiply times the area, multiply times 0.9. No. Phi's already there, okay? So don't multiply by phi twice, or it's not going to match your previous calcs. Sound good? Let's check and see if this works for the column that we just we did in those previous examples. So we're going to look at this column again. Let's sort of reorient ourselves with what's going on. So our strong axis is a single unbraced segment that's 35 feet long. It's fixed on the bottom. It's pinned on the top. For the y-axis, we have 3 individual segments that are 10, 15, and 10 feet long, respectively. They're all pinned, right, except for the section at the bottom that's fixed. It's a W14 by 90. It's 50 KSI, and we're going to analyze this accordingly. Sound good? Yes. You talking about these?
Yeah.
They are.
Well, I mean, yeah, but we don't take into consideration on the x-axis, right?
I'm saying there's nothing framing into it.
I know, but I feel like, would it, though, actually affect it? Like,
Oh, yeah.
buckle?
Oh, absolutely.
Okay, but we're not taking it into consideration.
No. And the reason why is because I've picked a column that's somewhat unique, and it's making you look at each axis individually. This column is not something that you would see every day, but it is a very common type of column in a given structure. Okay? For instance, take a look at the columns in the atrium here in this building, right? There's probably beams framing into them this way, but not beams framing into them this way because it's one big open space, right? Think like an atrium in a big hotel lobby or something, you know. So, you know, the main lobby's under here. So, you know, the main lobby extends, you know, what, 2 or 3 floors? But past that, you still got beams framing into it on the other direction. You see what I mean? Let me emphasize. If there were beams framing in on the strong axis, would it affect the capacity? Absolutely. Absolutely it would. Because you would have on the x-axis, if you had a beam framing in here and here, you'd have a brace here and here. And instead of having, you know, 1, 2, 3, and then 4 segments to look at, you'd have 6, right? Because you'd have, you know, another 2 segments here. And in that case, probably the y-axis would govern. See what I mean? Because if the lengths are the same and the boundary conditions are the same, well then, yeah, then the weak axis is going to govern. The strong axis only governs when the lengths or the boundary conditions are different. In this case, they are. But in the case you're mentioning, they probably wouldn't. Does that make sense? Those are good questions to ask. All right. Anybody else? This is good stuff. All right. Okay, now, so let's go back to this to this column. So, what's that? Typo on this. Oh, it's supposed to be method 3. That's a minor one. Maybe 4.25. Okay, so 5.25 there. 5.25. We're on columns, though. We're not on volts, so. I can admit that I make mistakes. I just won't admit how many. So. Okay, so let's recall a couple things. I'm making you all go back through your notes and through the manual, which I know everybody brought. So what was the area of this column?
26.5 inches squared.
26.5. All right. What was Fy again? And what was the maximum KL over R? 54.723. And that was, let's keep in mind, that was for the x-axis. Okay? All right. So what we're going to need is we're going to use table 4-22 to look up a phi F critical. Now, that table does not list a phi F critical for a KL over R of 54.723. So instead of looking up 54.723, what are we going to have to look up? 54 and 55. So help me out. Let's see. What is phi F critical for a KL over R of 54 and a phi F critical for a KL over R of 55? So what do we got? $36.4 what? KSI. And what's the next one? Okay, 36.1. All right, is everybody able to find that? Okay, that's important. I want to make sure everybody's going along with me. Is everybody able to find that? All right. All right. What's that? Now, we've got 36.4 and 36.1. I've got to believe you all can do the linear interpolation, or do we need to go through it and do it together? All right, so I propose that phi F critical for our KL over R of 54.723 ends up being 36.183. Does that sound about reasonable? Okay. So to compute the capacity, all we do is this. We take phi F critical and multiply it times Ag. So we take 36.183 KSI and we multiply it times 26.5 inches squared. Again, I know you see this calc and you're like, wait, didn't you forget a phi? No, I didn't. The phi is built into this value here, so don't add it, on top, or your answer is match. So what do we get here? So maybe like 9, so we'll say phi PN is about 958.9, about like that. Okay. Now, how does that compare to the previous two answers that we got? I mean, what did we have before? So, okay, so it's a little off. It's not leaps and bounds off, but it's a little off. Why is it off? Well, it's off because we're rounding and we've got linear interpolation. I mean, it's not exact. I mean, our column curve is not a straight line. It's very nonlinear. So there's a little bit of interpolation that goes along. And with that interpolation comes a little bit of error. This is, I mean, let's be honest. Your designs are, if they're being impacted by this level of rounding, then you're probably doing something wrong. Again, this is meant to be the gut check. This is really simple. This is really quick. If you're on an exam, again, looking at those column equations, they're long. They're long. And if you can do something pretty quick to check your math, do it. Okay? Make sense? All right. Any questions? All right. So if you understand that, then what I want to do is talk a little bit about design. Okay. So up until now, okay, I mean, when we've been talking about columns, we've been talking about column analysis. In other words, here's a column, it's this long, it's W14 by 90, it's this grade of steel. How strong is it? In other words, how much load can that column withstand before it fails? Bless you. Now, that's great and everything, but in design mode, we don't know what the column is. Our job is to pick the column. Okay, so what we're going to do is this. Remember this table 4.1, that available strength and axial compression? That is going to be our primary design aid. So first off, if you haven't tabbed table 4.1, I would do so. Table 4.1 is one of the most important tables in the manual, period. So regardless of this class, I would have that tab accordingly. Table 4.1 is what we're going to use to help select columns. Okay, now let me make a note. This table is going to be used not only for single columns, but for columns in frames. You know, well, what's the difference between that? The difference between the two is K, okay? K for single columns, we just look up. Remember, it was like 1 for pin-penned and 0.8 for fixed pen and all that. For single columns, we just look it up. What do we do for columns in frames? We use this, okay? In the end, though, we can still use this guide to design a column, okay? Make sense? Right. So here's how this works, all right? So, and it's pretty straightforward. So start off, we determine our design load. Pretty straightforward, 1.2 dead plus 1.6 live. I think by now that should be burned into the back of everybody's head, right? Okay. We're going to use table 4.1 to select what I'm going to call trial sections. This isn't like before where we select like one shape and do a bunch of math to verify that shape. We're actually going to have a family of shapes that we're going to assess. Now we're going to select those sections based on the weak axis capacity, but then we're going to have to go back and check the strong axis, okay? And when it's done, we might, for instance, we might find 3 different sections that work, and of all of those valid sections, pick the lightest, okay? So it isn't going to be like tension members where we have one member, we do this crazy amount of math to check that one member. No, we're going to have 3 or 4 different sections that we're going to check, and of all of those valid sections, choose the lightest, okay? Sound good? Now, a couple points. So we select based on weak axis capacity, and then we go back and check the strong axis capacity. This first example that we're going to do is only going to be selected based on weak axis capacity. The second example, we're going to go back and say, well, how would we check the strong axis capacity? So just bear with me on that. So that's my first point. My second point is in regards to what I mean by a family of shapes, or these trial sections. What you're going to want to do when you go through and select these sections is you're going to want to cycle through what I'm calling each family to find the lightest shape. In other words, when you're going through this iterative process, pick at least one W14, at least one W12, at least one W10, at least one W8, if you can. Sometimes, like for instance, you go through the W8s and there just isn't any shape that would work. Okay, so we'll cycle through a number of shapes to pick the one that works. Another thing, once you get your final answer, you should go through and check that answer using either the column curve or table 4-22, what we just did a few moments ago. because it's very possible that you made a mistake when you looked up the section. So you're going to want to go through and do the math to check it. Sound good so far? Don't worry, I think this will be pretty straightforward. Okay? Now, let's do an example of this. So I want to select the most economical column to resist a service dead load of 150 kips and a service live load of 350 kips. The column is 15 feet long, and it's pinned on each end in both directions. So this is sort of going to what you were saying, that if you had the same column with the same boundary conditions in both directions, well, then the weak axis is going to govern. Okay? But if the boundary conditions change, then you have to go through and check your strong axis capacity. Sound good? All right. So let's go through this process and see how this process would work. All right? Because I want you all to become very familiar with this table. I really want you to understand how this works. Now, can anybody tell me what the first step is going to be? Of course, yeah, factor the loads. Excited to factor these loads. If anything, you will remember by the time you get out of here that 1.2 times the dead plus 1.6 times the live is your factored load. What's that? Unless you have very high dead to live load ratios, yeah. Oh, getting ahead of myself. Now, what do we got here? 740. Y'all are just so excited to be back in steel design. Is that what it is? Okay. Now, our column is has a yield stress of Fy equals 50 KSI. Now, why is that important in relation to table 4.1? Like, why does that matter? Exactly. Table 4.1 is only good for Fy equals 50 KSI. So we needed to know that in order to validate that we could even use that table, which, don't worry, most wide flanges are 50 KSI anyway, so it's not that big of a deal. All right. All right, so Fy is 50 KSI. Now, let's look at table 4.1. So if you don't have your manual open to table 4.1, you need to go ahead and do so. Now, when you open your manual to table 4-1, if I gave you a column, let's say I gave you a W14 by 90 or what have you, how would you determine how strong that column is? In other words, what do you need other than the shape of that column to look up a strength? What's that? Now, do you need KL over R? You need KL. See, think about it. You couldn't calculate KL over R right now even if you wanted to. We don't have R because we don't have the shape, okay? But we can calculate KL, okay? Now, what units does KL need to be in? Feet. Okay, so how long is the column for this problem? 15. All right, K. K. How are we going to determine what K is? It's pen, so 1. There we go. So KL, and in this case we're looking it up in the Y direction, is KY, LY, which is 1 times 15 feet, which is 15 feet. Okay? Sound good? So far, so good. Now, this is what we're going to do. We're going to look up some trial shapes. In this case, because we're only looking at the weak axis, these are all going to be, valid designs. Okay, so this is what I want you to do. Let's start off with this. So let's start off with the W14s. Okay, if you recall, that table is only going to have W14s, W12s, W10s, and W8s. The reason why is because those are the eye shapes available in the wide flanges that are the most square. In other words, RX and RY are fairly close to one another, which means it's an efficient shape for a column. You're not going to find very many columns that are 30 inches deep. They're going to be fairly compact and fairly square. Okay, so I want you to go through the W14s. Now, keep in mind we're using a KL, a constant KL of what? 15 feet. And I want you to tell me what is the lightest W14 shape that will work. Okay, you say W14 by 90. Now, do I have a second on that? Now, hold on. What page is everybody on?
4-15.
4-15. So if you aren't on 4-15, get on 4-15. What's that?
I'm with them again.
Okay, we're on 4-15. Now you picked W14 by 90. Okay? Now why did you pick that? What was its VPN? 1,000. Okay? All right, what is the next lightest section after a W14 by 90? And what's its VPN? 735. So that is the lightest W14 shape that will work. Does everybody see that? Okay, so now, Mr. Fadiga, since you see, no, I'm asking you. Since you see this, tell me what is the lightest W12 that will work? We're going to get Mr. Fadiga on this. What is the lightest W12 that will work? Okay, 12 by 79. Do I have a second on that? Okay. Now you picked that because its VPN is what? Well, you all are well experienced on that. Yeah. I'll weld the column base plate on it. Sorry. All right. Now, somebody else, W10s. What's the lightest W10 that will work? A W10 by 88. All right. Do I have a second on that? Yes. Okay. Now, why did you pick that? All right. Now, bless you. What is the lightest W8 that will work? You're shaking your head. There isn't one, right? I don't. What's that? Special order. No, there are no W8s. Now, what I'm telling you on this example, because the strong axis and the weak axis both have the same boundary conditions and the same lengths, we don't have to check the strong axis. So because of that, all of these designs work. So if all of these designs work, which one are you going to use? Number 2, the W12 by 79. It's the lightest. It's the lightest. It is very possible. Okay, you're raising a very good point. It is very possible that this 12 by 79 could not only be the lightest, but also have a larger capacity than some of these heavier sections. It's very possible. Okay, it's all a function of just what is Rx, what's Ry, what, just what are the dimensions, okay? Very possible. Any questions? This isn't so bad, is it? Yes?
Why don't you have this table tabbed in your main?
I do. Hold on. I don't have a marker, so eraser drop. Oh, well, there's a little more to it. Yeah. There's a little more. Example 16b is gonna clarify it a little bit, which we're running a little short on time, so I'm gonna probably call it for example 16b. But let me just say something real quick. So the difference between example 16a and 16b is that with 16b we have different boundary conditions for the x-axis than we do the y-axis. On 16a they were the same. Okay, so on 16a, because they were the same, those sections that I picked, I know they all work. For 16b, that's not the case. Each one of those, section 1, section 2, section 3, they are all trials, and I'm going to have to validate every single one of them. Okay? Sound good? All right. I will see you all, some of you on Wednesday, some of you here in a few minutes. All right.